Welcome from Nexus. So, we're diving straight into the critique today, looking at part 6 of your material on big data solutions in the real world.
Right. It details how places like finance, public policy, healthcare use real-time streaming, advanced analytics, complex event processing, that whole suite.
Yeah, and the coverage is definitely broad. You touch on fraud prevention, next best action systems, lots of ground covered, which is great.
Okay.
But let's pivot straight to the critique for the computer science reader. We see a chance to add more technical depth, starting with the architecture.
Okay, architecture. I think I see where you're headed. The material gives us these, well, compelling use cases, right? Like the wind farm company monitoring thousands of parameters every second, making hourly predictions.
Sounds very impressive, yes. But what's missing, technically speaking?
Well, the key thing, the distinction we really need to make clearer, is the engineering trade-off behind it. The material does a good job categorizing by industry, sure.
Uh-huh.
But these real-world solutions, they'd be much stronger if they were properly grounded in specific distributed computing architectural choices.
So it's a bit too conceptual right now. We talk about distributed computing, yeah, and fast storage options are mentioned.
Exactly.
Mm-hmm. But those industrial examples, the wind farm, city traffic, they feel a bit disconnected from the underlying tech stack.
That's precisely it. Our main concern here is that it misses a key opportunity, especially for a technical pro. It doesn't really analyze that fundamental conflict. You've got high-volume, high-velocity data coming in.
Right.
And you need low-latency performance across a distributed system. That's tough. And the examples right now, they're kind of decoupled from the technical how. We need to force the reader to see the engineering compromises involved.
Okay. So how do we bridge that gap? What's the suggestion?
We think you should integrate the description of the business outcome, like the hourly prediction, directly with the specific tech needed. And often, these techs compete, right? Persistence versus processing.
Uh-huh.
You need to detail why one data path might be chosen over another. That architectural justification is, well, critical.
Okay, let's make that concrete. Back to the wind farm. Thousands of sensor readings a second, generating hourly predictions. That needs speed.
Precisely. So you need to clarify that decision. Is that super high-velocity data processed entirely in motion? Maybe using something like Apache S4? Built for that low-latency streaming analysis?
Or is it persisted first?
Yes, and if it needs persistence, maybe for historical context, that introduces a whole different set of technical costs and trade-offs. It's not a trivial choice.
And if persistence is required, then the engineer's looking at different NoSQL options, right? It's not just storage, it's about how you access it later.
Absolutely. Illustrate that trade-off clearly. Is the team storing that turbine data in, say, HBase, which is, layered on Hadoop, good for random reads-writes, low-latency lookups?
Okay.
Or are they pushing it all into HDFS, which is really built more for write-once, large-scale batch analysis later on?
Different tools for different jobs.
Low-latency reaction, think complex event processing, streaming analytics against the demand for long-term scalability and historical trending. That internal technical struggle, that's where the real value lies for this audience.
Got it. Integrating the what, the business outcome, with the why and how of the architectural constraints. That makes sense for CS folks. Okay, so architecture is settled, at least in theory. What about actually processing that data to get insights? Let's talk analytics.
Right. That leads us nicely into the second major opportunity here. The coverage of predictive models, cognitive computing, especially in those high-stakes areas like fraud prevention, it needs to go a bit deeper.
Okay.
Beyond just citing, say, proprietary systems and their capabilities, into the actual machine learning mechanisms at play.
So the argument is, for a technical audience, just mentioning something like IBM Watson and what it does, it's a bit too general. It focuses on the result, the what it learns, not the mechanics.
Correct. Our concern is that the material focuses maybe too much on the high-level outcome, the cognitive bit, and doesn't really tackle the critical technical challenge. How do you actually deploy these algorithms across petabytes of data? There's not enough discussion, we feel, on how traditional statistical models have to evolve, how they adapt to run efficiently on a distributed architecture. Just saying a platform can do something, well, it glosses over the huge computer science effort needed to get that speed and scale.
Right, showing the work. So we need to connect the dots better. Link the application result like next best offer to the nitty-gritty of deploying specific algorithms at that kind of scale and velocity. How do we do that?
Well, take the credit card example, using analytics for microsegmentation for next best offers. Great application.
Yeah.
But you need to explicitly connect that outcome to the practical challenge. How do you actually run, say, classification trees or logistic regression across, what was it, thousands of attributes and millions of observations?
That sounds like a massive computational job, especially the training part, right? It's iterative. You have to run over the data again and again. How does that even work in a real system?
That's the question. That's exactly what the material should be explaining. We suggest exploring how that iterative nature of model building, model training, where you're constantly calculating, adjusting parameters, how that gets parallelized.
Like across MapReduce or a Hadoop cluster?
Precisely, to get the speed needed for real-time engagement. So, for instance, with predictive fraud models, the reader needs to almost visualize how the calculation for a prediction gets split up, runs on maybe hundreds of nodes at once, and then gets aggregated super quickly for that confidence score. Show the distributed mechanics, not just the final answer.
Okay, shifting focus from what it achieves to how it actually achieves it at scale. That definitely boosts technical credibility. Now, the third area, this touches on something absolutely critical in the real world: trust, security, compliance.
Especially when you look at the most compelling examples, right? Healthcare, diagnostics, financial fraud detection. These inherently involve pulling together very different, often very sensitive data sources.
And the risk profile for a big data system is just different, isn't it? Because you're integrating so much so fast.
Exactly.
So the weakness we identified here is, well, the need for security and governance is mentioned, data quality too. But the real-world scenarios, the ones combining sensitive internal CRM data with messy external stuff like social media, they lack a focused discussion on enforcing security right at the front door, at the ingress point.
That's the absolute crux of the risk with high-velocity data. You're using tools like Flume-G, maybe, pulling in streams, and using that data for analysis before it's even properly landed or been fully vetted.
Right.
PHI in healthcare. Or even malicious content that just slips past traditional security checks because it's coming in so fast.
But isn't there a tension there? If you slow down the stream too much to do deep validation, deep security filtering, doesn't that defeat the whole purpose of high-velocity streaming? How does an engineer square that circle?
That's the challenge to address. We recommend directly linking the data integration tools, the ingestion strategies, directly to security best practices. You need to emphasize the methods for keeping data quality high and maintaining privacy within these real-time, often hybrid, data flows. The CS Pro needs to know where in the architecture to put those checks.
Okay, concrete steps then. How do you enforce this in real time?
Okay, first, when you talk about that integration stage, blending external data, really stress the principle of planning for consistent metadata.
So the rules get applied evenly.
Exactly. So governance rules aren't just for your existing, nice, structured data stores, but they apply consistently to these new streams as they come in.
And what about those really messy, unstructured streams? The human-generated stuff, call center notes, social media text?
Well, specifically, you should suggest that when using real-time ingestion tools, the architecture must integrate security techniques right there. Things like data anonymization or maybe tokenization.
Before it gets used downstream.
Yes, before that data, especially that sensitive, free-form text gets fed into the predictive models, it's about securing the data in motion. You can't just wait for it to land safely in some secure data lake somewhere. The speed of analysis is crucial, yes, but compliance, that's non-negotiable. You have to balance them.
Okay, that makes a lot of sense. So we've covered 3 big opportunities here to really strengthen Part 6, make it resonate more with a technically savvy reader.
Yeah, we started with urging that shift from just describing things conceptually to really grounding the real-world solutions in those specific architectural trade-offs. You know, making the engineer face the choice. low latency streaming versus high-scale batch persistence.
Right. Then we move to analytics, emphasizing the need to deepen that discussion, focus on the mechanism, show how algorithms like logistic regression are actually deployed, how they're parallelized across MapReduce or similar frameworks, not just stating the end result.
Exactly, the how, not just the what. And finally, hitting that critical point about governance and security. Specifically, integrating things like tokenization right at the high-velocity ingress point, connecting the tools directly to security practices to protect sensitive data in real time. Look, the core concepts you've laid out are solid, really good foundation. But refining this technical depth, weaving in these practical constraints, that's what will really maximize the impact for your target audience here.
Great points. So the invitation is clear. Take these actionable suggestions on board, refine the depth of those trade-offs, embed the security constraints right into your real-world use cases, and when you're ready, please do send the revised work back to us. We'd look forward to critiquing the next version.